Hey guys, it is good to sort of see you right now, at least work with you a little bit. I wanted to talk about some topics that we covered but didn't cover all the way in depth, so I can kind of clean up some topics. So this video or these series of videos are going to be specifically about cleaning up some topics. And so the topics that we're going to discuss would be as follows. So you see we've got finding the minimum and maximum values of linear programming. So that's going to be a big one. That might take the majority of the first video. Graphing points in 3-space, we talked about it. I just want to kind of confirm that. So that should be quick. Graphing equations and systems in 3-space, which is a little bit different. We didn't physically do that. We talked about it. So I want to make sure we do that. Representing translations, rotations and transformations, dilations and reflections via matrices. Sounds like a whole lot, but it's really straightforward. That shouldn't take too long. We're also going to discuss solving linear systems by inverted and augmented and row reduction forms of matrices. We did the row reduction. We can review that again, but I want to talk about inverted matrices and how we'll solve systems of linear equations. And finally, I want to talk about operations on functions, a slightly fuller picture. Really, there's two concepts that I don't feel like I went over as well as I wanted to, so I just want to make sure we cover that. So let's begin. Because we never actually covered the concept called linear programming, I'm going to ask you guys to think about or to conceptualize with me some vocabulary words. So one word that we're going to use is optimization, and basically that's going to refer to a process used to find a maximum or minimum for different quantities. And that sounds a little vague. Basically what's going to happen is we're going to get a set of constraints, maybe dealing with, I don't know, making cookies or something. And so, you know, a business wants to make cookies. They sell chocolate chip cookies at a certain rate. They sell sugar cookies at another rate. And what they want to do is figure out how much of each they should make in order to optimize profits, to maximize profits. Or sometimes you might be in a situation where you want to, I don't know, buy the cheapest something, but you need to hit certain price points. So let's say you want to buy the cheapest protein bar that has the right amounts of different types of vitamins, and you can compare the price versus the amount of vitamins versus the amount of fat or calories or whatever that you need to do. So that's some of the stuff that you would use optimization for. You want to figure out, given all these constraints, given all these concepts, what would be the best price, or what would be the maximum price or the minimum price. So linear programming is one strategy for doing that optimization. And what we're going to do when we talk about linear programming is that we're going to ultimately take our constraints, graph them on an XY axis so that we're dealing with, and I think we talked a little bit about this, we're dealing with linear inequalities, right? So we'll have a series of linear inequalities that overlap. And they will overlap and they will form what we'll call a feasible region. So I'm going to highlight that region that I just created by these imaginary linear inequalities. This is called a feasible region, and what we do is we're going to use this feasible region to actually determine what the maximum or minimum is, and that's basically what linear programming is. So that's the strategy we're going to use. So we're going to have a couple of things that we need to deal with. One is the objective function. The objective function is the function that we're going to use to maximize or minimize the situation. And it'll make better sense when we look at some examples. Just give me a moment. The other thing we're going to talk about is what are constraints. And as I mentioned, the constraints are going to be some inequalities that are going to give me the feasible region. So the cool thing is the feasible region is going to give us all possible values that fit the constraints. Okay? And so since that's a whole lot of values, we need to kind of figure out, okay, how are we going to determine what test points to use? Again, this is an XY axis, and it'll make better sense soon, but this is an XY axis where we're dealing with XY coordinates. But the cool thing is once you found the feasible region, you can actually use these guys. The vertices of that region are the only points that are going to either maximize or minimize your function, which is the optimization, which is not the optimization, the objective function that we're working with. Stay with me. All right. So the best thing is, I know vocabulary is a little bit abstract. The best thing is to actually use this vocabulary and these concepts in a problem. So we're going to do that right now. So this problem is a little boring because there's no backstory. It's just here's some information, do the optimization. So it's not as interesting as the next one, but let's take a look anyway. So here we're given what we have as the objective function, And this is the function that we're going to use to maximize. We're going to figure out how to figure out, given these constraints on X and Y, what is the point that's going to give me a maximum value for this situation. In fact, let's find the maximum and the minimum, right? So find the max and min. Find the max and min. Let me write that down. Okay, boom, there's a direction. So now what we need to do is kind of consider what's going on. How can we, so what we do is we take our constraints and we're actually going to graph them on the XY axis or the coordinate plane. And remember, these are inequalities, and inequalities, linear inequalities, is where we shade above or below the line. Sometimes we got a solid line or a dotted line, whatever. Here, all of these lines, by the way, are solid because these are less than or equal to or greater than equal to inequalities. If it was just greater than, obviously that would be dotted. You remember that? Okay, so we're going to graph this, and I'm going to take my time and do that. And if you have any difficulty with this portion, let me know. It's just something that we can go over. So let's get started. So here's my X and Y axis. And let's graph this first constraint of X being greater than or equal to 0. We know that the equation, the quick thought bubble, when we have the equation X is, let's say, equal to 0, that's basically a vertical line, right? Through 0 on the x-axis. So here we're going to have that vertical line, but it says x is greater than, so we're going to shade to the right. That's that first inequality. Let's take this next one, and I'm going to do this in orange. I'm going to solve for y and graph it because it's just easier to do so. So this is the equation I get when I solve for y, or the inequality, pardon me, that I get when I solve for y. And I like this because it's really easy to graph when it's in slope-intercept form. So I go up to 2 on the y-axis, and I rock a little -2, +3 as my slope, right? Because I recognize my slope is -2/3. And now the hardest thing on earth is I'm going to draw this line that, okay, that's not too bad. That's pretty good. I'm impressed with myself. Now, where am I going to shade? It says that y is greater than or equal to. I can choose test points in either region, but what I recognize is when it says y is greater than, I am above that line, all right? So I'm going to shade above the line. Now that I've done that, I'm going to similarly solve for this equation, or solve for y in this equation. So then after solving for y in this inequality, what I realized is that I needed some more space. So I had to go down and add a little extra. It'll be fine, trust me. Okay, so then y is greater than or equal to 3x minus 9 tells me that I'm going to go and grab, let me grab the color pen that matches that equation. I'm going to go and grab the y-intercept, which is -9, 1, 2, 3, 4, 5, 7, 8, 9, right down here, and I'm going to rise over run 1, 2, 3 over 1, 1, 2, 3 over 1, 1, 2, 3 over 1. And I think that's a good enough line. So now that I've got this line going on, I need to check out where I need to shade, right? And so it says shade greater than y, so that means above. So I'm going to shade above y. So after I do that, hold on. There we go. After I do that, I see that I'm getting a feasible region is starting to emerge. And so the feasible region is where all of the inequalities actually overlap. So I'm hoping that this last guy, and let's use, I don't know, this color here. I'm hoping that this last one is going to be, nope, not the right pen. I'm hoping that this last one is going to be beautiful and beautiful for me at this point means closes it off and makes a feasible region so we can get to the next part, which is testing these points and maximizing our equation, all right? Or max and minimizing our equation. So let's go ahead and try that. So first thing I want to do is solve for y. So y is less than or equal to, move the x over here, -x, divide everything by 4, so -1/4 x, what's that, +4. Yeah, I think that's right. So that's what happens if I solve for y, recognizing that my x-intercept is 4, or yeah, well, I shouldn't say so. I solve for y, I guess it's fine. All right, so recognize my y-intercept is 4. It's late, people. I'm sorry. I'm going to use my slope, which is down 1/4. 1, 2, 3, 4, something like that. I'm going to graph this like that. I know this isn't pretty. And the fact is, when you're doing linear programming like this, you really want to be neat. I'm really doing this just so you can see it, and I'm going to do a little cheating just to tell you what the real points are, even though my graph doesn't necessarily represent that. So my deepest apologies for that. All right, so now recognizing that y is less than or equal to, obviously a solid line because it's equal to, we talked about that. Now we're going to shade down, right? And so, as gorgeous as this is, not so gorgeous, as gorgeous as this is, I want you guys to really observe and let me look at this. This is my feasible region. This is the place where every constraint is satisfied within this polygon, right? And so the law says that if indeed you can find a feasible region, if you want to maximize that function given the constraints, what you're going to do is the maximum and the minimum will be found only at these corner points. So the reason why I said that it's necessary to be neat is because we actually have to figure out what the ordered pairs are on each of these corner points or vertices, and I'm going to tell you what those are right now. And so there we have, this point is 0, 4, this point is 0, 2, this one's 3, 0, and I think I could have gotten all that from my ugly graph, but this one I don't think I was going to get, and this point is 4, 3. So with all of that, so I had a little cheating, I looked at the answer book. Okay, so with all of that, after you get these corner points or these vertices, it actually is kind of fun because you're just plugging and chugging and checking your work. So what you would do at this point, let me get a smaller tip pen so I have a little bit space. What you would do at this point is go back to this function and you're going to try all of the corner points. And the answer that is the greatest will be your maximizing point. And the answer that yields the least value for z would be your minimizing point. So in each case, we're using the function z is equal to 4x plus 5y. So in a way, I guess I could do this. Copy and paste. Please paste for me. I'll paste it in a weird place. And I'm going to do another copy and paste. Let me just paste it again. Let's paste it again and paste it again. Why am I pasting it 4 times? Because we got 4 points to check. You figured it out. All right. So now I'm literally just going to substitute in each of these points. So if I were to, let's use a different color pen. If I were to plug in, let's say 0, 4. If I were to plug in 0, 4, what I would do is put my 0 in for x and my 4 in for y, and I see that in this case z is equal to, I never actually got that other color pen, did I? Z is equal to 20, and then over here if I were to plug in 4, 3, I would get in this case that z is equal to 4 times 4 is 16, 5 times 3 is 15. When I add it together I get 31. If I'm wrong, please don't be mad at me. Yeah, I think I'm right. And now if I put in 3, 0, you guys get that the answer here is 12. And finally down here, well, that was 3, 0, 4, 3, 0, 2 is the last one. If I do 0, 2, I get that the z value here would be 10. And so I can literally go through and tell very simply which one is the greatest one and which one is the least. So my greatest value is here, my least value is here. And so I'm highlighting these guys. So the point that gave me my greatest value was 4, 3. So this is my, use a pen, Dion. This is my maximum value. And the point that gave me my minimum value, which was 10, was 0, 2. And that will be my minimum. So I maximize and I minimize the function. Is that all right? So I think this actually might be a really good stopping place. I'm going to show you, and this is something we can talk about. I'm going to leave this as an assignment. That's what the teacher does the easy problem and then leaves you the hard one. Please don't be mad. So example 2 was crazy fun. I'll give you some time to look at this and talk about it, and I'll kind of give you an idea of what's going on. All right, so my hint to you is that we're going to let x be the number of units for product 1, y will be the number of units for product 2, and the function that you're going to maximize, and I'm getting all of this from this portion of the problem, the function you're going to maximize would be this. Here, you're going to come up with the constraints using x and y, and when you come up with those constraints, you need to graph that feasible region, and when you graph that feasible region, that's when you will figure out the corner points or the vertices that you can use to test. So I want you to try that, and I look forward to talking to you soon about some more linear programming and more stuff. All right, talk to you guys.